In this screencast, I'm going to explain what we did in the Week 10 class to get you caught up. So these were our topics: modern physics appetizer. The second was, does free fall acceleration depend on mass? And then we did two experiments, comparing interaction force pairs and modeling the force of friction. So for our little modern physics appetizer, last week we looked at Maxwell's equations, and we noticed that in those equations there were these two constants. And one of the things we talked about was that Maxwell's equations actually predicted a speed for the propagation of electromagnetic waves. And that's because doing a bunch of math with Maxwell's equations, you can come out with this expression for the speed. And these two values are both constants. So what we did in class was we put in the values for the constants and we calculated the speed of light. So you can pause the video and do that if you want to, or you can do it later. And that came out to 3 × 10⁸ meters per second. Our second topic was considering the free fall acceleration of a bowling ball and a feather. So in everyday life, we do not see those fall with the same acceleration, and that's because of air resistance. So the question is, if the only forces on these objects were the force of gravity, what acceleration would they have when they're falling? And we just had the scenario: suppose each object is dropped near Earth's surface, find the acceleration of each. And we did not actually do these calculations, but what we did was we wrote down Newton's second law, which is F net equals mass times acceleration. And then we rearranged that, dividing both sides by the mass. So we had acceleration equals net force divided by mass. And then we considered that the net force on each object would just be its force of gravity, the force of gravity due to its interaction with the Earth. So for the chicken feather, the force of gravity would be little m times g. And then to find its acceleration, we would have acceleration equals that force of gravity, so little m times g, divided by m. And the m's cancel out, and you just get the free fall acceleration of g. Then if we repeat that with the mass of the bowling ball, big M, once again, the force of gravity on the bowling ball would be capital M times little g. But then to get the acceleration, we divide that force of gravity by the mass, which is big M, and the mass cancels out. And so we get the same acceleration due to gravity. And so the reason that objects fall at the same rate of acceleration independent of their mass is that the force of gravity is directly proportional to mass, and because the force of gravity is directly proportional to mass, but the acceleration is also inversely proportional to the mass cancels out. So if you double the mass, you're going to double the force of gravity, but you're also going to have, which would tend to double the acceleration, but then because the mass also doubles, that would tend to half the acceleration, and so you end up with the same value. In the makeup folder, you can watch this experiment done using the link in the makeup folder. Our next topic was comparing interaction force pairs, and you already read through and worked through a document where you were prepared to think about these ideas and understand what the experiment is we're going to do. Before we actually did the experiment, we just talked through some of the concepts using these slides. So first of all, we reviewed what is an interaction force pair. And an interaction force pair is when two objects are interacting, such as the leopard and the tree are in contact, so we know they're interacting. They each exert a force on the other object. So the leopard is exerting a force on the tree, and the tree is exerting a force on the leopard. So that's an interaction force pair. In the situation with the cat or the leopard, we'll call him a cat now, there are 3 interactions. We have the tree interacting with the cat, and that yields 2 different forces. There's the force of the tree on the cat and the force of the cat on the tree. Those are the ones we already talked about, and I've color-coded that interaction red. Then we have a force of gravity, so we have the force of the earth on the tree and we have the force of the tree on the earth, and that's coded green. And then we have the interaction between the cat and the earth. We have the force of the earth on the cat and the force of the cat on the earth. So we have 3 different interactions giving us a total of 6 forces, but each interaction yields 2 forces. Now what we've done so far this semester is we have chosen a focus object and we've looked at all the forces on that one object. So suppose we choose the cat, then we can draw a free body diagram for the cat where we're drawing just the forces on the cat. So we have an upward force of the tree on the cat. Notice that's color-coded red for that interaction with the tree. And we have the force of the earth on the cat, which is blue. And the cat's at rest, obviously very asleep here. So these forces are balanced. If those are the only 2 forces, they must be equal and opposite, equal magnitude, opposite direction. So that's what we've done so far. That's a free body diagram. What we want to look at in this experiment, though, is not comparing different forces on one object, not comparing these 2 forces with each other, but comparing these forces, the forces that arise from a single interaction. So we want to compare how does the force of the tree on the cat compare to the force of the cat on the tree. And these forces are not on the same object, so we cannot use the idea that, well, it's at rest, so the forces must be balanced to figure out how the forces compare, because what object will we be talking about? There's 2 objects here. So the question is the force of the tree on the cat greater than the force of the cat on the tree? Is it equal or is it less than? So this is the question we want to answer in this experiment. So to make that a little more concrete, here with this picture, how do the forces compare? So here's the force of the tree on the cat, that would be upward, but then the cat exerts a downward force on the tree, and we took a little poll in class, do you think that the force of the cat on the tree would be less? Would it be smaller? Would it be A, arrow A here, as compared to the force of the tree on the cat? Would it be equal? That would be B. Or would it be greater? That would be C. So think of what your wild guess is. And then we looked at one more situation. What is the interaction force pair for a collision between a truck and a car? So a simplified system schema here. I left out normal forces and friction and earth. Just looking at the interaction between the truck and the car, 2 forces result. We have the force of the truck on the car, and we have the force of the car on the truck. And so how do those forces compare? If this left arrow represents the force of the car on the truck, then which of these arrows would represent the force of the truck on the car? Do you think the truck exerts more force on the car than the car exerted on the truck? That would be C. Or do you think they're equal? That would be B. Or do you think it's less? That would be A. So then we did this experiment together in class. And I am going to put up a separate document that goes through all of these steps for that experiment. So let's pause there.